I'm super excited to have with me today Dr. Steve Scheiner. He is a computational chemist out of Utah State, and he is an expert on a beloved topic in introductory chemistry, the hydrogen bond. He has authored close to 200 papers on the topic of hydrogen bonds and other non-covalent interactions. And in one of those, he teamed up with other scientists in an IUPAC paper that actually redefined the hydrogen bond. And I did not know that. So I am worried that for the last 10 years, I have been teaching it wrong. So Dr. Scheiner has been kind enough to make sure that I am teaching it correctly and then talk about what these changes mean for an introductory chemistry student. So Dr. Scheiner, you are a computational chemist. What does that mean, and why is that the best type of chemistry?
Well, computational just means instead of doing chemistry like you see in movies with flasks and Bunsen burners, we just use computers to do the research that we're doing. And so we can study a lot of molecules and atoms and interactions by using techniques that have been developed that are based on quantum chemistry, which I won't go into. But the calculations can be pretty tedious. That's why we use computers instead of pencil and paper. But they can also be quite accurate.
So you actually, that leads into a question I was going to ask at the end, but I'll ask it now since you brought it up. I noticed that you're on like a journal of international quantum chemistry and stuff. We do cover quantum mechanics very, very briefly and probably very poorly at the introductory level. It scares a lot of, I would say, high school teachers, and it probably scares a lot of high school students. How far can you get in the field of chemistry before you really have to confront the realities of quantum mechanics?
It depends what type of chemistry you do. So, for example, organic chemists who are concerned with building molecules and reacting one molecule with another, they don't really need to understand the details of quantum chemistry. But if you really want to understand what makes what goes into a chemical bond, really understand how these atoms are bonded together, then you do have to understand some quantum chemistry. So it's usually more along the lines of physical chemistry that you need to know it, more so than organic or biochemistry.
Yeah, I remember. I remember a lot of trauma from my undergraduate physical chemistry courses, but I see that you also teach that. So I guess that was probably because of the quantum mechanics. Now, you were a fellow of the IUPAC. And that was, I assume, the reason that you were involved with the paper on the hydrogen bond.
It's just every so often that organization collects a group of people who are experts in a particular field to look into whether they need to redefine or to refine some old definitions of certain terms. And back 10, 15 years ago, they decided the hydrogen bond had been so re-examined over the years that the original definition, which you see in high school and college chemistry books, is not wrong, but it's sort of outdated. It's too restrictive as compared to where hydrogen bonds occur. So there were a group of us, I don't know, a dozen or 15 of us, who come at it from slightly different angles. And together we put together what would be a broadened definition of the term.
So for people who don't know what the IUPAC is, what is it?
Well, it's international. That's the I.
Yeah.
And their idea is to try and serve as kind of a unifying body of chemistry. So it's sort of like the UN, where they don't have any executive authority. They can't pass laws in any countries, but they can sort of provide some guidelines that chemists can use. There's nothing mandatory about it. It's just if chemists want to see what's the latest on a particular field that's been developing, they might look at some IUPAC definitions.
So, let me restate, I guess, the classic introductory definition of the hydrogen bond. The pre-corrected definition, and then you can kind of tell me where you guys tore that apart and then rebuilt it. So, essentially, at the high school level, we define it as a hydrogen atom in a bond with a highly electronegative element like nitrogen, oxygen, fluorine. Those highly electronegative elements sort of pull the cloud away from hydrogen. Hydrogen being special, no core electrons, ends up with a rather strong partial positive charge. And that leads to an unusually strong dipole interaction with agreeable neighboring molecules. It is the source of liquid water. Water would be a gas without it. And we also talk about how it's important for biological structure and function. And so what was wrong with that definition, I guess?
Nothing wrong. That's perfectly accurate.
Yeah.
What's broadened about it is the atom that the hydrogen is bonded to doesn't have to be highly electronegative. So the ones you mentioned, yes, certainly they hydrogen bond with the H attached to it, but there are other atoms that can do so too. Sulfur, for example, phosphorus. So sulfur is right below oxygen, P is right below nitrogen, chlorine is right below F. And this is particularly important, it can even be a carbon atom. And I say it's particularly important because carbon is the basis of living things. Mm-hmm. And so the fact that the CH group can also form a hydrogen bond has some particularly important implications in biology and biochemistry. On the other side of it, what you mentioned were agreeable groups. And usually what that means is an atom with a lone pair of electrons. Mm-hmm. So water, the oxygen, has two lone pairs, which are good for, it's not just an electrostatic thing, as you mentioned, where the positive hydrogen interacts with negative. There's a quasi-covalent piece to it too, where there's a little bit of electron donation from the electron donor, the lone pair, to the hydrogen. And that electron donation is important as well. And so the source of the electrons, again, in general chemistry, you would teach the source of electron has to be a lone pair of N, O, or F, for example. Well, it turns out, again, the atom with the lone pair does not have to be highly electronegative. Chlorine, sulfur can serve in that capacity too. And it's not just the lone pair. In organic chemistry in the first semester, students will learn about a pi bond between the two carbon atoms. Well, that pi bond, the electrons in a pi bond, they're fairly detachable, or they can serve as a source of electrons, just like a lone electron pair could. And the other thing you'll learn about in organic chemistry is aromatic systems, where benzene is the classic example, where you have this sort of flexible pi system in a ring around a hexagon. Those flexible pi electrons are also a good source of electron donation. So to summarize, the broadening has been the atom connected to the H can be something other than Fn or O, and the electron source on the other side can be a lone pair, but could also be a pi bond, pi bonding a pair of electrons too, or an aromatic system. And then there's even other refinements which aren't so common, but metal atoms sometimes have electrons which they're not holding on to so tightly in a d orbital, which you'll learn about when you take general chemistry. Yeah. And those d orbitals can also donate a little bit of electron density to the hydrogen that's coming up on them.
Oh, that's fascinating. I'd never heard that before.
Well, you fall in the heading of 90% of research chemists as well. Most research chemists still live in the world of what they learned in general chemistry a generation ago. Well, so this idea of the more broad picture is just really coming into its own, not just in high school and college chemistry, but even in the world of research chemists as well.
Yeah. So there's actually two. I want to take that in both directions. You mentioned that at times, right, it acts like a quasi-covalent bond. So are we looking at sort of like a kind of like a smearing of like the boundaries? Like, is there a point where that the hydrogen bond, which we traditionally think of as like an intermolecular force, is really almost like right on the edge of being, I guess, a primary bond, like being a covalent bond?
Exactly. The border between non-covalent and covalent is a blurry one. So in the case of the water dimer, which is the classic hydrogen bond, interaction energy is on the order of 5 kilocalories per mole. So that's about 20 kilojoules per mole. That hydrogen bond can get stronger depending on the groups involved, particularly if one of the two groups has a full-grown electrical charge. And that can approach 70, 80, 100 kilocalories. And then you're getting into the territory of a covalent bond.
Yeah, So in fact, I guess I had known about like the fluorine, hydrogen, fluorine, but I thought that was only like 40. So you're saying that there are ones double that strength out there.
Yes. The one you're talking about, the FHF minus. Yes, that's the interaction between an FH and an F minus.
Okay.
And you're right, that's about 40 kilocalories. But there are some, particularly if both groups have a charge, a plus and a minus, that it gets even bigger. So for most intents and purposes, you could think of a standard hydrogen bond as non-covalent with a little hint of covalency to it.
Okay.
By covalency, I don't just mean the strength and energy, but the nature of it. That electron donation of a fraction of an electron, that's the beginnings of a covalent bond.
Mm-hmm. And so I guess on the other side of it then, right? So when you're talking about atoms less electronegative than the classic examples, what differentiates, I guess, a hydrogen bond in like a CH group from just other weak, what we would consider intermolecular forces like a London dispersion force?
That's a really good question. And that's one thing that chemistry research is wrestling with. So the idea of a CH hydrogen bond, I think it was probably around the turn of the century that it really started to gain a lot of interest.
Yeah.
And there was a question, just like you're putting it, is it really a hydrogen bond, or is it a sort of typical intermolecular force? And that's one of the places that calculations like I do came in.
Yeah.
Because you can dissect it into pieces. So there are little components of interaction energy. There's electrostatic, there's charge transfer, and things like that. So we could do calculations of a CH hydrogen bond and compare that to your trademark OH hydrogen bond. And you could show that all the trends were there. They might have been smaller, but the patterns were identical. So for that reason, we thought it was valid to call it a hydrogen bond. Yes, it's a weaker one, so it may only be, say, 2 kilocalories versus 5. But all the it's not just that, but the spectroscopic fingerprint, which has to do with bond stretches and NMR, which again, people will learn about in general chemistry.
Mm-hmm.
The shifts on the nuclei, the NMR shifts for a CH hydrogen bond were the same as the old standard OH hydrogen bond. So with all those pieces there, we thought it's quite fair to call it a hydrogen bond, albeit a weaker one.
Has there been, I guess, in the circles that you run, has there been pushback against that paper?
Yeah, in fact, for any women watching this, they'll find this interesting, that in the 1980s, I think, there was a woman crystallographer. Crystallographer are people who look at where the atoms are in a crystal.
Yeah.
They get the atomic positions. And from her crystal structures, she came up with one of, I think, the original proposal of a CH hydrogen bond. And a number of people just ignored her. And the current research into that research says it was sexism.
Really?
Because she was a female, they just wouldn't take her seriously. Well, 10, 15, 20 years later, guess what? She was right, they were wrong. So there has been pushback against the idea, certainly when it started off. But I'd say pretty much now the reaction is more like yours. It's not, people don't say, oh, you're full of it. They say, I hadn't heard about that yet.
Yeah.
So I think it's just a matter of people doing more reading and realizing that the concept has progressed.
So at the high school level, we tend to classify the hydrogen bond as like a really strong intermolecular force. And then we're always forced to put a little caveat saying, well, it could be, I guess, intramolecular, I guess, if the molecule is big enough. Should we be using a different term to cover like the broad umbrella of all of it instead of having to like...
Okay, intramolecular and intermolecular just means is the proton donating group and the acceptor group on different molecules, as in a water dimer, as in ice, or as in a protein. If you guys, when you take biochemistry, you'll see that the classic alpha helix, where the groups wind around into a helix, that helix is held together by hydrogen bonds from one part of that helix to another part of the helix. So that's intramolecular. So yes, intra and inter are still perfectly good differentiations.
What would be the, I guess, the vocabulary term that would be like next up that would cover both of them? Would you call that like a secondary bond, or is there a term you think that kind of covers both of those terms?
I think the term non-covalent bond has become a prominent one, but that comes with the caveat, as I said before, that even a hydrogen bond, if it gets strong enough, sort of blurs its way into the covalent side of things. But now that I've mentioned non-covalent bonds, I will throw you another curveball, which is, so the hydrogen bond, you have the hydrogen atom as the bridge, right?
Yeah.
Suppose you replace the H with something like a chlorine.
And that was going to be one of my follow-up questions. Yeah, you have research on, I guess, what would be like a halogen bond, right? Which is something else I had never heard of before. So go ahead, blow my mind about this.
Almost everything is like a hydrogen bond.
Yeah.
The reason it's counterintuitive is chlorine or any halogen is pretty electronegative. So whereas the hydrogen will have a bit of a positive charge, a halogen would have a bit of a negative charge. That's true. But the important thing is that the negative charge on the halogen is not evenly distributed. So here's the halogen, here's its bond to another molecule.
Mm-hmm.
Around here, sort of the equator, it's negative. But along here, the extension of the bond, it's positive. So we would say that the distribution is anisotropic. Very not isotropic, it's very unevenly distributed. So the positive tip here, and they call it, you may see the term sigma hole.
Okay.
This positive region on the extension of the bond, call this the pole, can attract a base just like a hydrogen can. So a halogen bond is in 95% of intents and purposes, just like a hydrogen bond.
So essentially, if you had diatomic chlorine, you could see that interaction is what you're talking about. And I guarantee you 100% of high school chemistry teachers would absolutely get that wrong. I don't think any of us has ever heard of that. So I guess generally speaking, then, like, I know that we use the term like chemical bond, chemical interaction, chemical force. Are these really, I guess, do these have a specific meaning in chemistry, or really are they just different ways of kind of getting to the same idea?
They're vague. Chemical force, personally, I don't really hear anyone calling it chemical force. Mm-hmm. Chemical bond, yeah, that's really used a lot. And we've been using it here a lot. But honestly, there's still some debate about what exactly that means. In the sense of general chemistry, well, a covalent bond, they share electrons. That's clear enough. But when you get into things where, like benzene, where I mentioned you have that aromatic thing, well, where is the bond? Is it here or here or here? It's somewhere within that whole circle.
Yeah.
So that language can be fine for many systems, but you can run into trouble for other systems.
So we should just be using the term chemical bond, but the word bond means a lot more than what we traditionally think.
I guess the way I would think of it or describe it is within a molecule, all those lines you draw between the atoms, mm-hmm. those are chemical bonds. They really are. And we could argue about some of the refinements of where it comes from, what it means, but we can call those chemical bonds. When two molecules come close together, I think you might call it an intermolecular interaction. I wouldn't call it a chemical interaction, although that wouldn't be wrong. It just might be a little ambiguous. So people who deal with those sorts of things would just call that an intermolecular interaction. Might be attractive, it could be repulsive, but it's an interaction between two molecules.
So based on that logic, then is the name hydrogen bond, and this was one of the original premises of my original video, is the term hydrogen bond then a good name, right? Should we be calling it a hydrogen bond, or should it be called like a hydrogen interaction to differentiate it from like a true bond?
Well, in language, you're always looking for short words.
Yeah.
And hydrogen bond, it's got a history of a century already. And people really pretty much understand it. So there's no reason to dispense with it. But it is important that people understand it's not a covalent bond.
Okay.
Got a little bit of covalency to it, but it's primarily an intermolecular bond with a strength of on the order of magnitude smaller than a covalent bond. But it's a perfectly good term, just like halogen bond is. Mm-hmm. It's not a covalent bond, but it's such a close analogy to the hydrogen bond that it makes sense. And by the way, you happen to, so you know the halogens. Do you remember the name of the column right to their left?
The chalcogens and the pnictogens, right?
You're ahead of a lot of chemists. There's also chalcogen bonds.
Yeah.
They're exactly the same thing, but they involve sulfur and selenium. Okay, let's test you. The column to the left of that.
So we have the halogens, the chalcogens, and then it would be like the pnictogens, right?
Yeah, the pnictogens.
So we actually say the P. I've never heard anybody say it, so I don't know.
I say it. You know, I'm not even sure how we're supposed to say it.
I just read all this stuff. I don't know.
I call it the Pnictogen bond.
And so shall I. Okay. You got two people in your tribe.
So not just hydrogen and halogen, there's a whole class. And the ones next to that, carbon, silicon, those are tetrals. So there's also tetral bonds.
And these are all getting down to a pretty small sort of strength interactions, right? No?
They can be quite strong. The strength of a halogen bond or a tetral bond can be as strong or stronger than a hydrogen bond.
So you study a lot of these, I guess, non-covalent interactions, right? Besides hydrogen bonds. So I know that hydrogen bonds, I guess, is the one everybody knows. Is there one of these in particular that you think more people should know about?
Probably halogen bonds.
Yeah.
Not because of anything fundamentally more important about them, but just applications. So in the field of medicine and pharmaceuticals, a lot of pharmaceuticals have halogen atoms added to them in one way or another. Fluorocarbons, chlorine has been added. So if you were to look at the molecular structure, probably any pill you're taking probably has some halogen somewhere in the molecule. And that makes the halogen bond more important than many of the others. So, and in fact, the halogen bond has been researched a lot more than the others. It's got a longer history. Whereas the others, Pnictogen, Chalcogen, tetral, that's only in the last decade or so that people have been looking at those more thoroughly.
Now, would you say like most of the ramifications of your studies is probably through like the pharmaceutical industry, or is that some of the biggest applications?
That's a primary one, but even in just general biochemistry. So in proteins, for example, there's methyl groups all over the place. And according to the ideas of tetral bonding, that carbon atom could interact with an oxygen similarly to the way an NH group. So an NH group would form a hydrogen bond with a carbonyl oxygen, but the methyl group just next to it could form a tetral bond with that oxygen. So that has a great deal of impact on how the protein folds itself, the structure of proteins. And that has nothing to do with halogens.
So you've been studying this now for over 4 decades, correct? And I'm sure, and I imagine that, I wonder how someone ends up becoming a specialist in this. And so can you look back on your life and see, back in the 70s, was there like a moment that you can pinpoint where like it was clearly where you began down this path of studying these specific hydrogen bonds and other molecular interactions?
I could trace it back. So when I started as a graduate student, I had to pick a research topic to explore. And the topic that I was exploring was the mechanism of a particular enzyme, how an enzyme, like a digestive enzyme, how it works. And as I was reading about it, I realized that an integral part of its mechanism involved these 2 hydrogen bonds between some protein residues, they're called. And as I researched this, and I was looking at the transfer of a proton from one side of the hydrogen bond to the other, I found that pretty interesting. But that was just a tangent of what I was doing. So then I finished my graduate work and started my own independent research career. So and then I was looking for a research topic. And since I had learned a good deal about hydrogen bonds in this graduate work, I decided, well, let's try doing a little research on it. And as I proceeded, I just kept finding it more and more interesting.
Yeah.
New and new wrinkles to it. And so it led into other things. So from there, I started working in CH hydrogen bonds. And that led me into these very closely related halogen bonds and chalcogen bonds. So it's been a sort of evolution.
That's amazing. Dr. Scheiner, I really do appreciate you being generous with your time and answering some of my questions about hydrogen bonds. I might come back for a second run at some point. But I think hopefully this is at least shown maybe some teachers that are watching or students that science is not like set in stone. Like the stuff in your textbooks is an evolving language, and there's things to be discovered. And I think, I appreciate you being on the forefront of that.
Yeah, well, it's my pleasure to be doing it. That's the fun of science, is just keep doing it and learning new things as you go. I can't think of any other profession that is as rewarding as doing science research.
Well, I think that's probably a good place to leave it. I super appreciate your time, and I thank you, and I wish you the best of luck in your research.
Okay, this was fun, Mark.
Thank you very much.
Okay, take care. Bye-bye.